Okay, we will start nevertheless, I think on time. So we're starting a new topic today. So we'll discuss what is called Schramm-Loewner revolution. So on one hand, we will use much of what was before. On the other hand, in a very self-contained manner. So it's if you had trouble with something, it shouldn't be much of a problem. So this is an object introduced fairly recently, less than 20 years ago, by the Schramm. And the question he asked, so the problem was to describe something like percolation. So he first asked for percolation or easing model configurations. But that is so that would be, well, for example, we do it on some lattice. So let's say we do it on hexagonal lattice, which is difficult to draw. So configuration in the easing model or in percolation is just a covering of hexagons in two covers. In percolation, you just cover them independently. In the easing model, you assign certain probabilities which depend to how many neighbors you have of different covers or the same cover. So that seemed to be to Schramm a bit too difficult to do outright. On the other hand, what physicists usually studied, physicists usually studied correlations of covers at 2 points or 3 points or 4 points, which seemed to be too little. So what he suggested is to study just one part of the configuration, to study interface. So the idea was that you take your model and you cover one half of the, well, maybe I will do it like that. You cover boundary to the left of 1 point in one cover. Up to some place. To the right of this point, you cover it in another cover. And then you study the boundary between these two covers. So the so-called interface. So for example, if I do this picture and no matter how I cover everything inside, there will be one interface separating yellow from blue, which runs from A to B. There might be some loops, but there will be one interface. So physicists sometimes call it domain law. So interface from A to B. So interface between yellow and blue. And so the interesting thing with this model is that I can cover everything and I can just draw this interface, but I can also do it as a conformal growth process. I can draw it step by step. So I can start drawing it step by step. So for example, I look at what is covered here. If it's blue, I turn right. If it's yellow, I turn left. Here I look if it's, for example, yellow, I turn left. If it's again yellow, again I turn left. So each time I just sample what is the next hexagon and I turn left. So I don't want to know and I don't need to know the whole configuration. I can just draw this by sampling one by one. And there are different models where it's sometimes easy, sometimes difficult. So for example, for percolation, I just toss a coin. Each time I arrive at a new hexagon, I toss a coin. If it comes yellow, if it comes heads, I turn left. If it comes tails, I turn right. Sometimes you can arrive at a hexagon which is already visited. So let's just imagine that you have this picture that we did this turning. So to arrive here, you only need to have these covers. So you see, for example, this we don't even care whether they're blue or yellow. It completely doesn't change our curve. So here I already know where to go because this part is already covered. I bumped in the boundary. I'm forced. I'm here. This is one place where I'm forced to turn right. So the question is, you have this. So what is an interface? It's a random simple curve gamma. So how to describe it? So that's the question which Schramm posed, that instead of describing the full picture, we just describe this curve. And then the hope is that once we describe one curve, we'll be able to do everything in some way or another. So for example, the loops which will be there. So for example, here you might have a picture like that, then you have a small loop. You can, for example, put someone on a place in a loop and then again describe it as a curve. So the question, how you describe such a curve, and if in the discrete setting you have a discrete random curve, so it's a probability measure on a random broken line. If you go very, very far from the domain, or increase the size domain and decrease the size of the hexagons, you should in the limit get a random measure just on some fractal curves which go through the domain. So the question is how to discuss these measures on the curves inside domains, on simple curves inside domains. Before we discuss measures on random curves, how to describe a random curve, let's try to describe a deterministic curve. So fortunately, there is a method which was invented 60, 80 years before Schramm. Well, Schramm reinvented it, but it turned out that it already existed. The reason why Schramm was able to reinvent it is that what physics strongly suggested to us, that physical intuition, that in models like percolation or easing, the curves which you get, the random curves, are conformally invariant. So if you want to draw a curve from A to B which is conformally invariant, there are various ways to do it. You can do, for example, geodesic and hyperbolic metric, or something which goes at a given angle from geodesic. But here you have a random curve, so it should be something random, but still it sort of suggests that we should play with conformal maps in defining this curve. And the way it was proposed by Loewner, so it's the so-called Loewner evolution. So Loewner published a few papers in Europe, including one about Loewner evolution, and then he, being Jewish and living in Vienna, he fled Nazis and changed the spelling of his name, O with umlaut, to O and E, and lived happily thereafter in Stanford. So he published a few papers like Karl Loewner with this spelling, and then many more as Charles Loewner with just spelled like that in the United States instead, on completely different subjects. So it's okay. So the Loewner evolution, the setup is the following. So we have a curve. So there are two setups which were usually done. So Loewner did the setup where there is a curve in a domain from a point A to a point B inside. So we'll be mostly interested in the setup which is chordal, which is between two points on the boundary. And then there is a radial setup. And then the suggestion, which, well, in principle, you can have more complicated. You can do, well, for example, you can draw like Riemann surfaces with some marked points, and you can draw curves on them, but then it becomes more complicated because you should look at the moduli of these surfaces and so on. So it's significantly more complicated, and there is no canonical way to do it. So we'll do first the Hordal case. It's more interesting for our purposes, though radial is slightly easier because you can use all the distortion theorems around point B, which is inside, and here point B is in the boundary. So the distortion theorems are slightly more difficult, and maybe I'll cheat my way out of it. So I will do it for simplicity for a half plane. So let's say half plane. So the domain omega is a half plane. Point A is 0. Point B is infinity. So you have, you should get a curve which goes from 0 to infinity of. For example, there was a slide I showed on the first lecture of this picture, slide by Schramm, where you have infinite array of hexagons, and half plane, half line is colored blue, half line is colored yellow, and then there is a curve separating the two. So what we do, we parameterize this curve in some way. So parameterize by time. So it's a curve gamma of t. Then we have a domain, let's say omega t, which is c plus minus gamma from 0 to t. So you draw your curve up to time t, so gamma 0 t. And one way to describe this domain is just to write a map, let's denote it gt of z, which maps it to half plane. So gt, so there exists by the Riemann mapping theorem map gt, which sends omega t to c plus. Even more so, there are, well, there are 3 parameters to fix, so we now have to fix 3 parameters. So there are two questions we have to settle. So it's how to fix, well, fix gt, which parameters what is mapped where. So that's how to fix gt. And the second is how to parameterize by time. So fixing gt, there are, well, I mean, there is an obvious way on both those two pictures that we are going towards point B. So we should fix everything around point B. So point B is at infinity, so let's fix everything around infinity. So what we do, so the answer to the first question is we take gt such that gt at infinity is equal to infinity. And we have 2 more parameters to fix, so I say 2 more is gt prime of infinity is equal to 1, and gt prime prime at infinity is equal to 0. Now, the second 2, they sound a little bit absurd because it's a point on the boundary. So I will just rewrite them normally, so it's maybe yeah, I was too fast to write that. Look, we have, let's fix gt so that gt at infinity goes to infinity. So what happens is that we map half plane with a slit. By the way, here one should understand that what happens with the slit, so it's kind of open up. So it is mapped to an interval here. And if the tip goes there, then the base point, there are two approaches to base point, and they go to two different points here. So the left part of the curve goes here, and the right part goes on the right, if the curve is simple. Okay, so what we can do, so the question is, of course, what do I mean by these two uniformizations? So let's for the second forget them. So let's do Schwarz reflection and define GT by reflection as a map. So let this be interval from P to Q as a map from so it was a map omega T to maps to C plus, and we can get omega. So omega T is this minus gamma 0 T. So we can get C plus minus gamma 0 T and its mirror image mapped to C plus minus the interval PQ. So what we do, we take a mirror image of our domain. So it looks something like that. Define our point as a image of a point as a mirror image. So the image of a point is the mirror of the image of its mirror. And we get an analytic map which maps analytically everything outside this curve and its mirror image to everything outside the image of the curve. So in particular, this map GT is analytic at infinity. So it's analytic at infinity, so the derivatives do make sense. So in particular, GT is homomorphic at infinity. So if it's homomorphic at infinity, we can write, and infinity goes to infinity, so we can write that at infinity GT of Z is equal, we can write a power series expansion. Since infinity goes to infinity, it will start like A1Z plus A0 plus A minus 1 over Z plus A minus 2 over Z squared plus so on. Yes.
The map, when we extend it,
yes.
From C, not C plus, no?
Well, yeah. C, yeah. Yeah, of course, yeah. Thank you. Yeah, so it's. So there is this expansion. By the way, immediately a remark or a proposition. Maybe I must have it somewhere later. So it's immediately, let's say, proposition 0 that all these coefficients aj, they are all real. Why? Because the real line is preserved. So if you have a function which preserves real line, once you do the Taylor expansion at infinity, all these coefficients, there are some derivatives. So derivatives of a function which goes real to real will be real. So because GT of the real line, it's inside the real line. So all these coefficients are real. And now what we can do, we can subtract this coefficient so that it's 0. And we can divide by this coefficient so that it's 1. So take nu GT, let's say nu of Z as GT of Z minus A0 divided by A1. And if you write its power series expansion to be Z plus, well, new coefficient A minus 1 prime over Z plus A minus 2 nu over Z squared plus so on. So this is how we fix two parameters. And A1 and A0, they are exactly, well, this is exactly saying that A1 is the first derivative. So this is what I meant there. that this is the A1 coefficient and this is the A0 coefficient. So if you check, those are exactly the derivatives. Okay, so we fix these two coefficients, so we have this map. It turns out that actually, this coefficient plays some important role, and I want to first say a few properties of this coefficient. So let's say GT of z is equal to z plus, I denote this coefficient alpha of gamma over z plus small order terms. So this coefficient alpha, so this coefficient, I say that it's alpha of gamma 0t. So it's a sort of capacity like parameter. So actually it's just electrostatic capacity in a half plane. So capacity like parameter, so the real capacity is approximately logarithm of it. So if I do electrostatics in half plane and I put unit charge at infinity and minus unit charge on this curve gamma, then this coefficient will give me exactly the capacity, and I make the electric boundary of the half plane. Now I want a few properties of it. So the first property is that it very nicely rescales. Yeah, okay, I already said that alpha is real, that I already said. But also, if I rescale curve gamma, and actually it's well defined not necessarily for a curve, it can work maybe for any set. So I can draw here not necessarily a curve, but any set subtracted from the plane. So it's also works for any set k. So the general setup could be that there is a set k which borders on the half plane, and I have the map, let's say gk, and gk is z plus alpha of k over z plus etc. So the first one is that alpha is real, and if I rescale, if I increase the set by a factor, say, of 5, then alpha increases by a factor of 25. So alpha of k times increased, let's say r times increased set k is r squared alpha of k. So what happens is if I increase this set twice, how do I write gk? Well, g for r times k of z, to write it, I need to take gk, but evaluate it not at z, but z over r. So I need to shrink z back. But then if I plug in gk of z over r, the first coefficient will be 1 over r. So I need to multiply by r. And this will be r times z over r plus alpha of k divided by z over r plus so on. So I take product, so it will be z. And the second term I take product, it will be r squared alpha of k over z plus so on. So hence this formula. There is, by the way, some sort of superficial resemblance to Brownian motion. So Brownian motion in time t goes square root of t away. So here capacity diameter r is capacity r squared. So if you have capacity t, diameter is square root of t. So here there is something which numerologically fits well with the Brownian motion, that it kind of has the same scaling, and it will come in handy later at its it's actually the reason why what Schramm did made sense, that this object has, so Schramm put into Loewner evolution Brownian motion, and the reason why this led to some object is because of that scaling. But let's maybe work out two examples. What is this capacity, just to understand better. Generically, this capacity of the Loewner evolution for a given curve are very, very hard to write down. But there are some cases where it's easier. And the first example is what happens if my curve is just a slit of the length, let's say, yeah, let's do it the length, what would be good? Square root of t. So it's I square root of t. So how do we map this guy to a half plane? To map it to half plane, we can take the map z squared. You take the square, so the result will look like that. So this interval will go to the interval protruding from 0 to the left, and I square root of t will square to minus t. So this minus t. Then you can map this thing by z plus t to a half line which starts at 0. And then you can employ square root of z to get here. So you will get a map which again opens this up. Now this was t, so it will be 2 square root of t square minus square root of t. So this is an example where it's easy to work out. So the map in this case is square root of z squared plus t. Which you can easily expand. So g t of z is equal to square root of z squared plus t. Now if you expand square root, well, it will be z, well, it will be z times square root of 1 plus t over z squared. So what do wait a minute, did I do it correctly? Yes, and this thing is 1 plus approximately 1 plus half of that t over 2 z squared. So it's approximately that, and then so what you get is 1 plus t over 2 z plus small order terms. So if the interval has height square root of t, then its capacity is t over 2. So it's alpha of this interval is equal to t over 2. Now two more cases where it's easy to work out, and I'll leave them as an exercise, which so the first one you already have seen, and the second you almost have seen. Suppose that example, exercise number 2. Suppose that we have an interval which is at an angle, and specifically, let's say that the interval is at an angle theta. So it's let's say that it's in interval from 0 to a point theta to the power theta times 1 minus theta to the power 1 minus theta times e to the power I pi theta. So theta is between 0 and 1. So this angle is theta pi. So this is the simplest Schwarz-Christoffel mapping, which you can write as an integral fractional polynomial of fractional powers. But in this case, it looks well. You can write it in a nice closed form. So what happens is that so I'll just write the answer. So if you take map G and you take inverse map F to half plane, it turns out that you have a map which maps 0 and to the tip. And two approaches to this point, it maps to the points, well, no, maybe, I maybe map it not to 0, but to twice theta minus 1, theta and minus 1 minus theta. Yeah, because I want coefficient infinity. So I will just write an answer that f is z plus 1 minus theta to the power theta times z minus theta to the power 1 minus theta. So this is sort of an exercise to be discussed in the exercise session. And that already you can expand. And if you expand, you get that f is approximately z minus theta 1 minus theta over 2, 1 over z plus so on. And then g is equal to z plus theta 1 minus theta over 2, 1 over z. Yeah, by the way, a remark is that if f and g are two inverse maps, then these coefficients are plus alpha and minus alpha. So this is just an easy, well, I think it will be next property. It's an easy exercise that when you compose such maps, this coefficient is additive. So f and g, they compose to identical maps, so these coefficients are negative of each other. So what is the conclusion? So the conclusion is that if I take this interval of length 1 at the angle of theta pi, so alpha of such interval from 0 to e to the power I pi theta, I can calculate. Again, it's an exercise. So what should I do to calculate? I should take this number, but I should remember that I calculated for the interval of a different length, so I should use this rescaling. So the exercise is that the formula is theta to the power 1 minus theta over 2, 1 minus theta to the power 1 plus theta over 2. So what's, well, it's not important what this formula, well, okay, that's basically the most complicated situation where you can calculate. Anything more complicated than an interval, well, there is also a sort of logarithmic tie spiral where you can calculate, but besides this, you can never calculate because it's just too complicated. You can't write a conformal map. But the interesting thing about this formula is that what you notice, and this is a really important remark, so if theta goes to 0, then alpha of this interval, let's say k, goes to 0. Or if theta goes to 1, then alpha of k goes to 0. So what happens that if you take interval of length 1 and you rotate it closer to the line, then alpha goes to 0, which is logical because you map to half plane, you map half plane with a slit which is at an epsilon angle. So there should be basically no difference between half plane and that. Of course, you can say, look, there is a very long length 1 fjord. So what happens to this length 1 fjord? And to this length 1 fjord happens the following thing, that this interval will be mapped, we know precisely where it will be mapped. And when theta, for example, goes to, let's say, theta goes to, so in this case, to 0, then what we'll get is that two of these points, they will collapse. So this fjord, so the entrance to this fjord, in the limit will be mapped to something very, very, very small. Because from a conformal observer which stands in the conformal plane, it's something basically almost not visible. Because to enter this fjord, you need to go through a very, very thin strait, and you never reach the end. Well, you reach the end in exponentially large time. So indeed, for conformal map, for Euclidean geometry, this is very different from half plane because there is this length 1 fjord. But for conformal geometry, it's not very different because it's very, very small. It's almost not visible. So for example, Brownian motion in half plane doesn't enter this. It enters this with minuscule probability, very small. So this is sort of an important thing which is causes some troubles for us later for the estimates, that you can draw a curve of diameter 1 in Loewner revolution, but from the point of view of conformal map, it will be almost invisible if it's close to the boundary. So to do something visible, you need to go away from the boundary. So this is one example. So for example, if I start drawing a curve which goes left right on the boundary of a plane, conformal map doesn't change at all, because I don't change the domain. If I go epsilon away, it changes a little bit by epsilon squared. So it's the further you go, the further it changes. So to really have something noticeable, you need to go basically distance 1 away. Okay, and one more estimate. So this is sort of a generalized Zhukovsky map. So there was this Zhukovsky map which mapped disk to an interval. So let's do a two-step thing. Suppose I have an ellipsis. So for example, well, let's for simplicity say that it's point 0, it's point 1 plus k, this is point minus 1 plus k, and this point 1 minus k. So this is, well, I times. So this is the two half-axes are 1 plus k, 1 minus k. And then you can map it to a circle by a map z minus k over z. Wait a second, no, this is the other way around. So this goes to map z plus k over z. It takes the point 1 to point 1 plus k and point I to point I minus ik. Yeah, that's correct. This, in turn, can be mapped by a map z plus 1 over, that I always mess up, z plus 1 over z. Let me maybe just draw it on a different side. Z plus 1 over z. This can be mapped to half plane. So this is the Zhukovsky map. And we can also write inverse maps, but if you write inverse maps, then you have to solve quadratic equations. So you will have square roots. The inverse map here will be, let me see, do I write it correctly? Z plus, no, maybe it's in the other way around, z plus 1 over z. No, correctly, yeah, z plus 1 over z. So for example, when k is equal 1, well, this is a particular case of this map with k equal 1 when you have a completely flat ellipsis. So the inverse map solves the quadratic equation, so it goes z plus square root of z squared minus 4 over 2. And the other one is z plus square root of z squared minus 4k, probably 4k over 2. So the exercise is that the map G, this whole map G, you can write down. So the exercise is that G of Z is equal to something. Particularly, it's equal to Z plus blah, 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 1 minus K times 1 over Z plus so on. And moreover, you can do it in a more general setting. You can write this, you can assume that you have an ellipsis which has dimaxes A and B. You can always rescale it to the first one. So A and B, you can rescale it by a map Z times what it be 2 over A plus B. You can get into the realm of the previous picture. You can get 2 half-axes, 2A over A plus B and 2B over A plus B, and this is 1 minus twice B minus A over A plus B plus A 1 plus, sorry, a minus b over a plus b, and this is the same as 1 minus 2 a minus b over a plus b. So this is played the row of k. So in this case you can also write g of z, and you can, I again leave it for the section with the exercises, and I think it will be b times a plus b over 2, 1 over z plus so on. So there are some cases when you can calculate this capacity. So here in the second one, the important remark is that if b goes to 0, then alpha goes to 0. So if you make an ellipsis of the same width, but it's thinner and thinner and thinner, then its capacity goes to 0. And it's logical because our domain goes and closer to half plane. So essentially this is sort of the main estimate, that if I have grown something which can be included into ellipses with the axis b and a, then the capacity size is estimated by b times a plus b. So that's the estimate. And the biggest capacity you get if you just draw something orthogonally, because then you get b squared, so it will be, or a disk, so it's if you really go off the plane. So this is about this capacity. It's not really needed, but it is needed, but it will be much nicer with understanding capacity, what I'm going to write for the Loewner evolution. So I need two more properties. So the next property is that capacity is composition additive. So alpha is composition additive. So what I mean is that suppose that I have one set K and I add set L on top of it. So it's like there is a cactus and there is another cactus growing from it. So there is this map GK which flattens K and which takes L to a new set. So this set is GK of L, which is, say, I call L tilde. And then there is a map GL tilde which flattens this one. And there is their composition G K union L. So GK union L is composition GL tilde with GK. Now you compose two maps which go like Z plus alpha of L tilde over Z plus etc. composed with Z plus alpha of K over Z plus etc. Now if I do composition like, I plug in this here, I get Z plus alpha of K over Z plus etc. I plug in this here, plus alpha of L tilde over Z plus alpha of K over Z plus etc. If I simplify this, the first term will be alpha over Z, and then there will be small order terms. So it's Z plus alpha of K over Z plus alpha of L tilde over Z plus O capital 1 over Z squared. But on the other hand, this is Z plus alpha of K union L over Z plus small order terms. So we get a conclusion that alpha of K union L is alpha of K plus alpha of L tilde. So that's composition additivity. Now, as I said, I'm cheating a little bit. In the beginning, I promised to cheat. I said that if you do Loewner evolution towards point inside, you can write all the distortion theorems near this point inside and everything in terms of how far you are from this point. Now, the problem is that what we are doing, we are going towards infinite point, which actually lies kind of at the end of real axis. And if we go following the real axis, we can have very small alpha, but still reach the infinite point. So there is this tricky thing, this O capital, it's in terms of the diameter of our curve. So it's very easy to write O capital in terms of diameter of our curve because we did this reflection principle and expansion near infinity, but it's not in terms of alpha. So there is a slight complication if, for example, you decide to write a book about Loewner evolution and you want to do rigorous proofs of theorems. Then you need to show, you need to write this, you can write it as a formal power series, but if you write it really with an estimate, then the estimate is in terms of the diameter of these two compact sets. So it's not in terms of the coefficient alpha, it's in terms of the diameter, which it might be alpha is small, diameter is big. And that's a small problem, because you have to take into account diameter that you can have alpha, which is very, very, very small, because you are following the half plane, but diameter very big, so the estimate is not so good. So it generally means that kind of there is no nice estimates where it only in terms of alpha, and alpha plays the important role later. So that's the only tricky point, but not for this lemma. It's just O capital in terms of the diameter of this guy. Okay, and the last property of GT of alpha is that it's positive and monotone. Well, last two properties, so to say. Proposition 4 is that we already know that alpha is real, so that we already know. But actually, alpha is non-negative. And moreover, if k is not entirely inside the real line, so if k protrudes even a little bit, so if you have non-trivial, so meaning that G is non-trivial, G is not identical with Z, then it means that alpha is strictly positive. Well, physically it makes perfect sense. Of course, capacity is strictly positive. Capacity measures more or less how much charge you can put with a given bound on the potential, but we have not proved that this is indeed electrostatic capacity, so we can't use physics intuition. Well, we can use, but it doesn't give a proof because we haven't proven that it's physics capacity. So we'll do a proof with some trick, and that watch is ahead of time, or no, it's not. It's mine. It's behind. Wow, interesting. At one point, we had for a long time that this clock was ahead of time, and the one in the hallway was behind. And my theory was students put it that way so that professors finish lecture earlier but start later. But okay, let me just do the proof of that. So the proof is rather easy. So I will do what this map f of z, which has inverse minus sign, and it maps this to k, and I take the mirror image, and here is an interval which is mapped to it, and then I just use a primitive complex analysis how you determine this coefficient. So this coefficient. So this coefficient minus alpha will be equal to the contour integral of f of z 1 over 2 pi I, and I can take any contour which goes around infinity. And because exactly if you just integrate analytic function around contour, you get 0. But if it is meromorphic, you get exactly how many you get 1 over z singularities. And I take the contour which is the easiest possible. I take the contour which goes like that. So it's the contour which goes near infinity. So here the image will be this sort of heart shape in this particular case. And gamma has two parts here, gamma plus and gamma minus. On gamma minus, what do we have? dz. Yeah, maybe, you know, maybe even I also write that alpha is real. So it's just a real part of this guy. So it's 1 over 2 pi I, imaginary part of this guy. So 1 over 2 pi imaginary integral of the imaginary part of f dz. And now look, here dz on gamma minus, dz is positive because I go to the right. But imaginary part of f is negative because I'm in lower part. And on gamma plus, it's the other way around. dz is negative, imaginary part of f is positive. So when I take the product, positive times negative or negative times positive, I get something negative. So I get that this is strictly smaller than 0, so meaning that minus alpha is smaller than 0, then alpha is bigger than 0. And when it's non-trivial, I get some non-trivial integral. So capacity is indeed positive. Yeah, let's take a break of what happened with my watch. And maybe, yeah, maybe it's better to finish off in a good place. That immediately implies two properties. So the proposition 5 is that alpha is monotone. So the bigger the set is, so if I take one set and I take a bigger set, then for bigger set alpha is bigger because of the composition property and because of positivity. So the proof is proposition 3 and proposition 4. And also it's continuous in K. And continuous in K, it's because when you vary K by epsilon, you can include in the ellipses, the difference into small ellipses, and small ellipses has small capacity. So so the proof, again, you think about it to have some training and you walk through it on the exercise. So the proof is combination of ellipses and propositions 3 and 4. 3 plus 4 plus ellipse estimate. Okay, let's have a break and I fix my watch. Okay, so before we start, the takeout from the first half was that we take maps of half plane minus something and normalize them near infinity, and that there is capacity which grows as we grow set and grows continuously. And the only problem with this capacity is that if our set follows the line, then it grows very, very slowly. So there is this sort of problem. If I were to do Schramm-Loewner evolution not towards infinity, but towards point inside the domain, that would have been much easier. So, but the trade back would be that the formulas are slightly more complicated than we have here, and then it is less interesting for the growth phenomena we are interested in. It's sort of less applicable. Okay, yeah, should I? So now we can define the Loewner evolution itself. So the okay, that's enough. So the setting is the following. So we grow a curve gamma of t. It will be eventually something more general. You can imagine just a more general family of sets which is growing, but the important that at any given time they grow at one point. And then we have this curve gamma t. We say that kt is gamma from 0 to t, so this is the set kt. Rather, maybe I make immediately small remarks, so rather kt, well, more precisely, kt is the how of this curve. So what do I mean? Suppose that I have a curve which was growing, and then touched the boundary, and then touched itself, and then went off. So what happens for a conformal observer who stands in the plane? He does not see these two regions inside the curve. Doesn't see at all. So the conformal map doesn't see them. So the how, it just is the component of infinity of the set C plus minus gamma 0 t. So this is, no, I could say omega t is component infinity of this, and this is C plus minus omega t. So here, this is the set kt, and this is domain omega t. So you should notice a small remark is that suppose what happens when I am about to close this loop. So this bay, it's visible to my conformal observer, but as it becomes thinner and thinner, this straight, it's less and less visible. So for conformal observer, it doesn't, for Euclidean observer, it just vanishes like that. Just you click the points, it touches, and the whole thing of diameter 10 centimeters vanished. For conformal observer, it vanishes continuously because it becomes small and small in conformal metric. You see it, it's small and small, you almost don't see it, and then it vanishes. So for conformal observer, omega t changes continuously in this case. So if you map it to the map by the map gt, so at this time, for example, this place is mapped to something like that. Now when I continued, it's this bay is mapped to something small, and when I closed, in the limit it collapses to 1 point. So for conformal observer, it's very, very small. It's basically well, the size of the image, and is the probability that the Brownian motion enters here, and it becomes very thin. The probability tends to 0. Okay. So this is sort of an important remark, is that all formula we write, it's not in Euclidean metric, but in the conformal metric for observer who lives in this plane. And then when we're about to close, this is very, very, very small. So he doesn't care because he basically doesn't enter it. Okay. So this is the remark. Now, well, so it's, let's say kt. I draw it without difficult things. So we have the map gt of z. Which is expanded at infinity at z plus alpha of t over z plus smaller order terms, so well, alpha of kt if you wish this capacity. And now there is one more parameter we have. We can look at the tip of this curve, where this tip goes. And where the tip goes, I go wt. So wt is gt of the tip of my curve. So if the curve is nice and continuous, then the map, well, it's actually Carathéodory's theorem that the map can be extended continuously to the boundary. If it's a more complicated object, one has to work more, but well, that also can be done. So this is now the Loewner equation is. So the Loewner equation is that the derivative in C of my type derivative, let's denote it with a dot, gt of z is equal to derivative of the capacity divided by gt of z minus wt. Now, we'll of course prove it, but before I do some remarks, of course we know that capacity grows continuously, so we can change reparameterize time, so that alpha of kt is identically equal to twice t. So we change time so that our curve, we say time t, is when capacity is exactly twice t. So that alternatively, that means that gt of z is equal to z plus twice t over z plus small order terms. Well, you can ask why number 2. Well, Schramm decided to put number 2. It's, in a sense, it makes sense because if you take formula for radii case and then you collapse the point to the boundary, then you get number 2. So that's a more profound reason. So in this case, this equation is just g time derivative of z is 2 over gt of z minus wt. So it's a very, very easy equation. And essentially, what it says is that if you have an evolution of the map and you know where the tip went at each stage, you can reconstruct the map by solving this equation. So if you know at every, not at a given t, but at every t, if you know where the tip went, then you can reconstruct your map by integrating this equation. Now, well, that's the good news. The bad news is that the equation is nonlinear, and generally you cannot integrate it. For orthogonal slit, you can easily integrate it. For slit at angle theta, you can integrate it because you can write formula. And there are a few more cases when you can integrate it, but generally, if I give you wt, you won't be able to integrate the equation and get an exact solution. But you can prove some theorems. And some theorems are difficult to prove. For example, if I give you wt, which is C1 smooth, you can prove that you always get a simple curve. But if I get you wt, which is half C1 smooth, so like Brownian motion, that type of smoothness, further 1/2, a priori it's very hard to understand whether you get a curve or not. You might get some strange things. So the other thing which is maybe important is that the fact that it's nonlinear doesn't admit an easy solution. It also leads to the fact that some complicated, interesting things can happen. If it were something easily integrable, there would have never been some interesting phenomenology. Well, a few remarks I want to make before we prove the Loewner's theorem. First remark is that what is the role of wt? So the usual analog, well, for example, the Euclidean analog would be the following: that if you drive your car, you turn your steering wheel. So suppose you drive your car at a constant speed of 2 miles per hour. If you know the position of the steering wheel, you can reconstruct the trajectory of your car by integrating some equation. Because if you know position of steering wheel, if you know up to this time trajectory, you know where you are, you know your vector of speed, and if you know the steering wheel, you can solve how it will changes later. So that is an easy equation. Now, on the other hand, here we have exactly the same thing, only it's in hyperbolic geometry. So our speed is 2 hyperbolic miles per still Euclidean hour, and we solve this equation. It's more complicated, but we can solve and we can get the trajectory. On the other hand, if you have trajectory of the car, you can follow it with the car and you can see how the steering wheel turns. So there is a reverse problem. So there is kind of a bijection between curves gamma and this trajectory is wt. So what it means in our particular case? In our particular case, it means that if wt is if wt is at 0, then you just draw orthogonal slit. And you can write an exact formula. If wt moves to the left, you draw a slit which turns to the left. If it moves to the right, you draw a slit which turns to the right. If you want to draw something wiggly, you just take WT, which goes like sine, left, right, then you get trajectory like that. If you want to have something fractal, you need WT, which is really fractal, like Brownian motion. Of course, if you plug in random WT, you get random curve, and that is what we are coming to next week. So that's what Schramm did. Now, even if WT is not smooth, my map does not change very much because it has expansion which always starts the same. Only this point goes around. But there is another way you can write a map. Sometimes it's more convenient to map it so that tip is mapped to 0. So it's a map which we will denote by G capital T of Z. So it's GT of Z minus WT. So it's Z minus WT plus alpha of T over Z plus small order terms. So what's nice about this map? Well, the nice thing about this map is that you always grow at 0, so always the point is 0. And the other nice thing is that if you rewrite this equation, then the equation will be, for the new map, will be GT time derivative is equal to time derivative of G minus time derivative of W. So it's 2 over GT minus time derivative of W. So it's a slightly easier equation. So the problem with GT is that if WT is not smooth, if it jerks around, then GT will also jerk around. So it won't behave as nicely as the other map GT, but the equation in some cases is simpler. It's simpler to work with this parameterization. Now the second remark is that what does this thing or well that thing do? So if I plot, if I take WT and I plot the vector field 2 over G T minus WT, then you have a vector field which goes like that. Well, maybe let me just draw it to scale. So if you draw, well, no, it's better to scale, yeah. So if you draw this vector field, it's basically a hyperbola. It will trace hyperbolas. So if you put a point and you assign its time derivative to be equal to that, you have trajectories which are basically hyperbolas. And what happens on a vertical line, that points on the vertical line, they go faster and faster as they approach WT. And then in finite time, they hit it. Because here you have 1 over x singularity, which blows up, which integrates to infinity. Now the points which are just a little bit off, they go faster and faster and faster, then they very fast fly by like comets, and then they fly off to infinity on a hyperbola. And the points here is the same. So this is the main problem working with this equation, is that if you are near this tip, so if it's basically when you grow the curve, if you are in a point here and the curve can hit it, and then its image will hit WT and there is no more solution. Or it can pass by and then it speeds off. So the problem is that denominator can be small, so the fraction can be large. So we might not be able to write an estimate if we are close to WT. So this is why there is non-trivial thing in the first place, because there are points through which this curve passes. They just hit the real line at this point, and they cease to solve the equation. So this is what is going on. So if WT stays constant, then you just solve along the hyperbolas, and points above it will eventually collapse. If it moves around, then depending on how you move around, you can collapse it. Now, what can happen? if Wt is not continuous. Suppose that you had Wt which was sort of continuous, and then it jumped, and then it jumped again, and then it jumped again. So what will happen is that while it's continuous, we'll draw a continuous curve. But when it jumps, we'll start drawing a curve at a new place, which corresponds to the image of Wt at this point. Then when it jumps again, we'll start drawing again. When it jumps again, we'll start drawing the fourth part, and so on and so on. So one way, if you want to draw a tree, is to just have Wt which is jumping. Another way is that what you also can do, you can write a thing which goes, for example, like, let's say, alpha 1 over g minus Wt1 plus alpha 2 g minus Wt2. So what will happen is that there will be 2 points where you will be growing continuous curves, and their speeds will be alpha 1 and alpha 2. So this is another way how you can try to grow dendrites. Just put several terms like that on the right. In principle, you can even have integral terms, so it grows everywhere. So you can have things like integral with respect to some measure, let's say mu of w, g of z minus w. So for example, you can try this thing. Unfortunately, it doesn't work very well. I can say it doesn't work that well. I can say that so far it hasn't worked very well. People try getting interesting structures in that way, but so far there is a dozen of papers, and it's related to some, in random setting it's related, for example, it works very nicely if you take Dyson-Brownian motions, but I haven't seen something really spectacular with this. Okay, now I formulate the Loewner theorem. So there is a bijection so there is a bijection between Loewner chains, continuous Loewner chains, and continuous driving forces Wt. So I will call it driving force. Now Loewner chain is sort of slightly more general than curves. So you can have all the continuous curves, but you can have some other things too. And it's given, this bijection between these two is given by the solution of the Loewner equation. Now I have to say what a Loewner chain is. So in principle, I could leave it as this, saying that just it's slightly more than curves, but I want to maybe just say what are the examples. So, okay, the definition is very easy, so I'll just say the definition. So Kt is a Loewner chain. Well, let's say is a continuous Loewner chain. Loewner chain, if there are two properties, is that if it grows continuously for a conformal observer. So for this little man who lives in the plane, it grows continuously. And for example, what this means is that, that for every tau and every epsilon, there exists set A epsilon such that union of kt for t smaller than tau with A epsilon disconnects k tau from infinity. And also that the diameter of A epsilon tends to 0 as epsilon goes to 0. Maybe not k tau, let me just be k tau plus epsilon from infinity. So what it means is that suppose that this is the set k tau, and this union is slightly smaller than k tau. It doesn't include its closure, so it might be, for example, if k tau was closed like that, it doesn't include this point. So what I mean that there is a sequence of sets A epsilon, which goes something like that, which separate whatever you want to grow here. So if this is k tau plus epsilon, you can cut it away from infinity by a small arc. It doesn't mean that k tau plus epsilon is small. For example, you can have a picture which goes like that I have grown something which goes like this. So there is this set, and then well, for example, this is the set k tau plus epsilon. So you see, I add in epsilon time, I add a very, very big thing. But I can cut it off by very, very small set A epsilon. So I can grow something Euclidean big, but for conformal observer it's small because there is you can build a very small dam which separates this bay completely. Well, and then the second thing is, of course, since diameter tends to 0, you can define like WT is basically GT of the well, limit, let's say, limit as epsilon goes to 0, GT of A epsilon, so where this shrinking thing MIPS. So the second condition is that WT is continuous. You can formulate it here in some sort geometrically. I don't want to go into details, but here you can also formulate it that this is epsilon for tau, and for tau plus delta, they are very close to each other. So you can also formulate it geometrically, but that requires already half a page, so I don't want to get into that. Okay. So let me just prove this theorem. It's not a very difficult proof. So let's first go from WT, we go to a chain. So I give you a continuous driving force, I put you in the car, and I ask to solve the equation and get me the compact set. So how do you do it? We solve the equation GT time derivative of z is equal to 2 over GT of z minus WT. So we solve this equation. Now we define time at a point z as a supremum of times tau, such that g tau of z minus wt is bigger than 0. So we solve this equation, and of course, as long as denominator is non-zero, we can solve it. So it's an ordinary differential equation, continuous everything. As long as gt hasn't hit wt, we can solve it, no problem whatsoever. So the only problem which can arise is that these two things collapse, and then the right-hand side blows up, and we cannot solve it. And kt is the z in half plane, so that the t of z is smaller than t. So basically, now we just have to do ordinary differential equations to show that everything is fine. And essentially, well, there are a number of observations. So there is, first observation, that there is a unique solution of this equation on the interval 0t. Well, 0 t of z. Why? Just it's an ordinary differential equation. The right-hand side is not infinity, not 0. Everything is fine. So it also doesn't blow up. It's not 0. So there is a unique solution. Everything is good. Now, this solution depends analytically on the original position. So the solution is analytic or holomorphic in Z. So this is again the usual theorem about stability of differential equations. If you have a, well, Hölder coefficients in differential equation and you change point in the Hölder way, the solution changes in the Hölder way. If you have an analytic coefficient and you change point in analytic way, then you have analytic solution. In holomorphic case, you can just check that there is a complex derivative. You can just take derivative with respect to z, complex derivative. You can differentiate the right-hand side, so it's a fraction, so minus 2 gt prime of z, gt of z minus wt. So there is a complex derivative which you obtain by solving this equation. This is actually another important point, that if we later work, we can not only determine function g, but we can solve for g, and then we can solve for g prime and determine g prime. And that's important because g prime, for example, it tells us what is the distance of z to the boundary by Kirby distortion theorem. Okay. The solution is univalent. So solution is univalent. So z1 is not equal to z2 means that gt of z1 is not equal to gt of z2. Now this is a bit tricky because you start asking, well, well, maybe some suggestions. So how do we show that 2 points, their solutions don't collapse? So what could have been the problematic picture? That we have 2 points, we were solving this equation, and their images, they were moving, and suddenly they collapse, and then of course they flow as one from there on. So how to outlaw that two solutions collapse? Well, Try what happens if we reverse the time. If two solutions collapse, it means that for reverse time, there is one solution which splits in two. And this equation is basically time symmetric. So reversing time, just changing sign to minus here, and it's the same ordinary differential equation. So the proof is that reverse time, so you get equation, the same equation, g bar minus t of z is equal to minus 2 g minus t of z minus wt. If two points different, it means that their reverse trajectory is different. So it basically means that if gt of z1 and z2 are different, then z1 and z2 also are different. Oh, no, wait a second. I'm running a little bit ahead of mine. Reverse the time, yeah, that I'm already proving the next part, sorry. So I will erase it. So reverse time, there is a unique solution. There is a unique solution. There is a unique solution. So it means that there is basically, so the map G to gt of z, or if you denote it u, this is to g minus t of u. So it is a one-to-one, it is a bijection, yeah. Now gt is a map, univalent map, from C plus minus kt onto C plus. Yeah, I was running too fast and I already proved that. So how do we do it? So to prove that it's univalent map, we need to show that for all the points, all the points outside kt, we can trace their trajectories. So if I take, for example, these 3 points, I can trace their trajectories till time t. And what I want to show is that for all points in C+, I can trace their trajectories back. So I can take any point in C+, it should be on a trajectory of some point under this flow gt, so I should be able to trace its trajectory back. And that is again for what you can reverse the reverse time. So we take some point u in C+, solve the reverse equation, till time t, get g minus t of u, so we denote it by z, and then gt of z is equal to u. Now you can ask a question. This equation we could not solve for all the points, but why can we solve the reverse equation for all the points? There is one crucial difference. And the one crucial difference is that for what was this velocity field for my equation? It was going towards the line, and you could smash into point wt. Now suppose that I take the reverse equation. What is the velocity field for reverse equation? It's the same field but reversed. So the field goes like that. You always go away from the real line. So if you go away from the real line, you can never hit it. So the important thing is that if you look at this part, the imaginary part of this part is always positive. So here we use that the imaginary part of minus 2 of u minus wt for u in C plus is always positive. Because you take a number in upper half plane, you subtract real numbers, you get number in upper half plane. When you take reciprocal to number in half plane, in upper half plane, you get number in lower half plane. And no, you take a reciprocal to a number in, wait a second, so you take a reciprocal to number in in upper half plane, you get number in lower half plane, and you take minus, again you back to upper half plane. So you always go up. So that means that you that the right hand side is bounded away from infinity, because you never, denominator never crashes to 0. So we can solve forever. So with Loewner evolution, there is this sort of a tricky thing that people I mean, first oscillate between writing for G small and G capital. It's not much different, so that's basically the same equation. But also there is this profound difference when you solve it in reverse time and in forward time. Because if you solve it in forward time, what happens, you have a compact sets, when you solve in forward time, you have these compact sets which collapse. If you solve in reverse time, you have these compact sets which grow out of the plane. So if you solve in reverse time, every point has a trajectory, but there a new set appears on which there are points which have no past. So here some points don't have future, here some points don't have past. So it's the other way around. Okay, what do I have to prove? Do I have to prove something? Yeah. So I have to prove that KT is a Loewner chain. Yeah, of course, yeah. So I have to show that KT is a Loewner chain. So the set KT is a Loewner chain. So that is basically easy enough. First, C plus minus KT is connected, and even you can prove that it's simply connected. So this is just because you have a map GT, which is nice and continuous up to the boundary. GT from C plus is KT. C plus, so this is a nice continuous up to the boundary map. Then KT, so this is the first part, KT is bounded. So this is just because WT is continuous and hence bounded. WT is continuous and bounded, so if you solve ordinary differential equation and you bound everything there, you can see that you can eat up only bounded part of the thing. Now alpha of KT is equal to twice T. Why? Because we have, on one hand, we have that 1 plus alpha time derivative of KT over Z plus small order terms is the time derivative of GT. So this is here, I just use that GT is Z plus, what's the power series expansion of GT? It's at infinity Z plus alpha of KT over Z plus small order terms. And on the other hand, the time derivative of gt is 2 over gt minus wt. Wait a second, I got something wrong. Yeah, there should be no 1. Yeah, there should be no 1. Yeah, of course, because time derivative of z is equal to 0. Yeah, so this when you time differentiate disappears, and this does not. Yeah, and that on the other hand, you can again expand 2 over, you can plug in z plus alpha over z plus minus w plus small order terms, so it's equal to 2 over z plus small order terms. So you get that equating coefficient alpha over z plus small order terms is 2 over z plus small order terms. So alpha time derivative is equal to 2. So alpha is equal to twice t. And that's, I think, is about it. Yeah, and it grows at one point. Yeah, of course it grows at one point. There are properties that it grows only at gt inverse of wt. Well, you can just set exactly what is a epsilon to be, for example, gt inverse of, well, I don't know, circle of radius epsilon, for example, of circle of radius epsilon around wt, something like that. Okay. So this is just the proof that if I have driving force, I can solve equation and I get a thing. And in the remaining 2 minutes, I will outline the reverse proof. So suppose that we have the house, and we want to deduce that there is an equation. So from a chain to wt. And then we'll do the details later. So it's we set gt of z to be c plus minus kt to c plus. So we parameterize by capacity. Parameterize by capacity. So it means that gt of z is equal to z plus twice t over z plus small order term. So that we can do because it's monotone and continuous. And then basically the idea, so I will do it in the details next time, is that you want to take the time derivative of gt. So time derivative of gt is gt plus epsilon of z minus gt of z over epsilon, well, limit thereof. So this is the limit. I write this is a composition of a map gt epsilon of gt of z minus gt of z over epsilon. And now here, for this map, I use this power series expansion, which we always use. Now it looks a little bit illegal because I use it not at infinity, I use it for a finite point. But using for fixed time at infinity is the same as using at finite point for epsilon time. So it's this sort of rescaling. So you write that it's a limit of gt of z plus 2t over to this epsilon time to epsilon over gt of z minus wt, because here you need to recenter this map plus small order terms minus gt of z. This cancels out over epsilon, then epsilon also cancels out, and you get it's 2 over gt of z minus wt. So that will work out next time. So strictly speaking, it's a bit non-trivial. In a disk, it's very easy because you do Kirby estimates and you normalize everything around the center. Here, what I'm going to do in a week, I'm going to cheat a little bit. I'm going to write that this O capital is depends on alpha. It doesn't depend on alpha, it depends on the diameter, but actually, well, maybe I write that it depends on diameter, just then you require like 7 more minutes to do it. But basically, this is the thing. And you see the miracle which happens sort of here is that, so we have a conformal map of outside of some hull. And then you add something small to this hull. And you ask how much does it change? And theoretically, you can envision that you add slit in direction 35 degrees. It changes by something. 25 degrees by something else. It turns out, no, there is no difference. It always changes by the same thing, and the only parameter is this WT where you make the change. So it's kind of a little bit in parallel to the universality you have for the Brownian motion, that you can try different random walks, they still converge to the same Brownian motion. You can try a random walk which does two steps to the right with some probability, one step to the left with another probability. Or you can write that it jumps all over the place, but in the end you can only get Brownian motion which has two parameters. What is the speed of the drift and what is the diffusion rate. So here it's sort of the similar phenomenology. Actually, well, in principle one can even try to make some meaningful parallels, that there is kind of a universality. You don't, when you make a variation of a conformal map, there is essentially only one parameter where you variate it. Yeah, so it's, well, it's kind of in this Loewner formula, what is the infinitesimal change in conformal map if you make a slit at one point. Okay, so what do we do next time? We just rigorously prove this theorem. We can do, for example, some application. We can, for example, prove Loewner's theorem that a third coefficient is no more than 3. It's not a very long calculation, like 20 minutes. And then we will introduce the Schramm-Loewner evolution and discuss what it has to do with the random growth. Namely, what happens if you plug in WT, which is random. So, okay. Yeah, I think that's it for today.